So welcome everyone. Thank you for joining us on our Technical Friday webinar, today titled StreamWatch Trends. I'm Steve Tordo, the Director of the Science and Stewardship Departments for the Watershed Institute. And with us today, who's our presenter primarily today, is Jian Smith. She's our StreamWatch program coordinator. And today we'll be going over some of the things that we do to collect data, and a little bit of how we're beginning to work with what we have as we feel is a pretty robust data set of 30 years of collecting water quality parameters. Next. So logistics, we are recording, so we'll send you the recording in a follow-up email, and it'll also always be viewable through our YouTube channel. If you have any questions, please use the Q&A feature. I believe primarily we'll be waiting until the end so we can address some of those questions, just so we can keep things moving. But we'll try to leave plenty of room at the end to discuss some of that, because there's definitely stuff to discuss. Thanks for participating. For those of you who are joining, just everyone who's joining to watch, who's going to watch later, and who's going to participate in that discussion later. Thanks. We always want to take a moment to recognize that the land and water that's now under all of our care, belong to someone else before us. In our area, it is the traditional ancestral territory of the Lenni Lenape. We pay respect to Lenape people, past, present, and future, and their continuing presence in the homeland and throughout the Lenape diaspora. We respect their knowledge, culture, and tradition, which have contributed to conservation of land and water. Next, please. The Watershed Institute, if you aren't familiar with us, has the mission of keeping water clean, safe, and healthy. We work to protect, restore our water and our natural environment in central New Jersey through conservation advocacy, science, and education, but also in a statewide and beyond way manner as well, through some of our statewide programs and interstate collaborations. Next. We use our scientific monitoring and investigation, as we'll share a bit about with you today, to support our advocacy for protection and restoration of water and watersheds, and to support our environmental education. And we use our reserve and any lands and projects that we're part of to model best stewardship practices, particularly at our Watershed Center and on our 950-acre watershed reserve, which if you haven't visited, please do. Thanks. Finally, I'll draw your attention to our next upcoming Technical Friday, which is on November 11th from 12 to 1:15 as well. And we'll be going over one of the studies our Watershed Watch Network has initiated over the past couple of years on statewide road salts. So you can register today for that. But with that, I'll turn it over to Jian to present our StreamWatch data.
Thank you, Steve. Hello, thank you all for joining us today. And if you had signed up in June and waited all this long, thank you extra. My name is Jian Smith. I am the StreamWatch program coordinator here at the Watershed Institute and a member of the science team. And I have now been here a full year, so I can't use that as an excuse anymore. So for this presentation, because we're going to be going into some graphs and data, I'm going to actually not be on video, but I will come back for the Q&A. So let me just turn that off real quick. All right. So here's a quick overview of what we're going to talk about today. We'll start with the StreamWatch program itself, how it got started, what we do. Then we'll do a little bit of an overview of the state of our water here in New Jersey as a whole state, but also more locally. Then we'll start diving into the data. We'll talk about what kinds of data we collect and why we care about it, and what our data is showing about the state of our water right now, or over the past 5 years. And then we'll take a look at the 30-year data set and dive a little bit deeper to try to tease out any patterns and trends that might be in that data. Finally, we'll talk about some of the limitations of the program and the data that we've collected, and then we'll finish up with a little pitch on how you can get involved. All right, so here we go. This is the 30th anniversary of StreamWatch. The Watershed Institute as an organization was founded in 1949 by a group of environmentally conscious locals. So they worked to learn more about their water quality and what is impacting it and how to keep it healthy. So as part of that mission in 1992, the StreamWatch program was launched, beginning with the CATS program, which is the Chemical Action Team. And so since 1992, we have had volunteers going out and monitoring several different chemical parameters throughout our watershed. Of course, chemistry isn't the only thing. So in 1995, we added the BAT program, which is the Biological Action Team. And so this team has since 1995 gone out and done macroinvertebrate monitoring throughout our watershed. In 99, we had we started a rats team, which was the River Action Team, but that was dissolved in 2011. But in between, we started the BACT team, which unfortunately we couldn't figure out like a cute, funny acronym for that one. So it's just BACT. That's the Bacterial Action Team. And so since 2007, we have been testing local waters for bacterial contamination as well. So we couldn't be StreamWatch without talking about who we are. So in addition to myself and other watershed staff, we have a whole suite of volunteers, people aged 16 to 86. We've got scientists, some who are currently working, some who are retired. We have students, we have teachers, we have, backyard birders and naturalists and people who work on their municipal environmental commission. Sometimes we've got whole families that like to go out and just have a reason to get out on the stream once a month or once a week, depending on the team, and also community leaders. And these are just a couple of our long-term volunteers here along the bottom. So thank you all if any of you are here. Thanks for joining us. So these volunteers are the heart and soul of this program, and they're super dedicated. We do require a 1-year minimum commitment to participate in StreamWatch. And so I wanted to throw this up. This graph is actually a couple years old, but I wanted to point out how many volunteers we have that have been doing this for over 20 years, 15 to 20 years. Now we do have a lot of people here that have volunteered for less than 4 years, but most of those are kids who are leaving for college. And so we hope that with their experience with StreamWatch, they are going out into the world and continuing their maybe water quality monitoring, but at least their environmental interest and advocacy. So why do we care about water quality? Mostly because we like to use water. We like to use it for swimming and drinking and fishing. And also because, other animals like to use it, so other aquatic life. So most of the time, so we're measuring water quality as a way to protect and restore those uses of our surface waters, but also to help identify any kind of issues that might be happening. So we can, by collecting this data, we can try to tease out where pollutants might be coming into the system, and what can be done, and if what has been done is working. So before 2018, this was our StreamWatch monitoring network. We worked mostly in the only in the Stony Brook Millstone watershed. So you can see here, these incorporates Princeton, Montgomery, East Windsor, some of Ewing, but not too much. In 2018, we expanded into the lower Delaware watershed here. So these green sections here are sub-watersheds. So this was the expansion in 2018, and now this is what our current network looks like. It's a lot of data on this one little map, but all the orange spots are our sampling sites that are currently active. That's for at least one of the teams. Yeah, so I actually didn't even count how many this is, but it's quite a few. All right, so there are 3 ways to monitor water quality. The first of which is visual habitat assessments. So when we're going out there, we're looking at the streams to get an idea of what the positive and negative influences of those streams might be. So in this bottom picture here, you can see it looks like a pretty healthy stream. There's lots of trees, there's lots of rocks. We got a run or a pool here and a riffle over here. And in this picture here, we can see what looks like some significant erosion. We've got some undercut banks over here, and lots of sediment deposition over here. So, so this tells us a little bit about, what's going on in this stream, and is one of the more basic ways of monitoring our water quality. Next is doing the biological sampling that I mentioned before. So we take a look at benthic macroinvertebrates. We'll break that down a little bit. Benthic means it lives on the stream bottom. Macro means that you can see it with your eyes without a microscope, although as some of our BAT volunteers will agree, sometimes a microscope is really helpful. And swoop. Sorry, just a second. And invertebrates, which is of course organisms without a backbone. So these organisms can include insect larvae, as well as leeches, worms, crayfish, snails, clams, and lots of other little things. So when we're sampling macroinvertebrates, what we're looking for is a diversity of organisms. So these organisms have been studied and assigned a pollution tolerance level, which helps us to determine the long-term ability of the stream to support life. So they're broken into 3 categories. There's the pollution-sensitive macroinvertebrates, such as stoneflies and mayflies. There's the pollution-neutral macroinvertebrates, such as crayfish and damselflies. And then there's the pollution-tolerant organisms, such as scuds and leeches. And so what we want to see is really a combination of these 3 different categories to indicate a good level of biodiversity and health of the ecosystem. So that's what our biological action team does. They go out in the spring and in the fall of each year, and they're assigned 1 or more sites, and assess the water bodies for biological health and diversity. So they're doing a visual assessment as well as collecting a biological sample. Yes. So here's what they do. They collect the bugs using a D net. That's what's pictured here. See that D. Then they come back to the lab and they sort through everything that they've collected and pick out all of the bugs, and then they will identify them. Occasionally, we will also send those samples out to a certified lab for identification to a more precise genus or species. So the last type of monitoring that we do is chemical and or bacterial monitoring. And this is particularly important because it can give us clues as to what's going on in the water, where pollutants are being introduced, and what those pollutants might be. So right now, our chemical action team uses something like this, which is a Lamont chemical kit. And it's kind of a, you add a dash of this and a little bit of that and come up, it's a lot of colorimetry. So we're looking at colors to determine different levels of nutrients or pH, or we'll talk about that more. We can also use continuous monitors, which is this one on the right with the solar panel, or handheld meters, which is here on the top left. Then we also have the ability, more recently, we have the ability to actually analyze some of these samples here in the lab to get some more precise measurements. So we can look at that a little bit closer in a bit. So like I was saying, chemical parameters can give us clues as to the potential sources of impairments. So the chemical parameters that we're looking at include temperature, nutrients such as nitrates and phosphates, pH, dissolved oxygen, and turbidity. And our chemical action team goes out once a month on the third weekend of the month to measure these 6 parameters and to help us assess the health of the stream. And so this, like I mentioned before, is the team that started in 1992, and that's the bulk of our data, is this chemical data. There's also the the bacterial action team, which is the newest, again, started in 2007, and monitors bacteria populations weekly throughout the summer months. So from late May to late August, we have volunteers going out once a week to collect water samples, which are then brought back to the lab and analyzed using our equipment here for both E. coli colonies as well as nutrient content. And most recently, we have had our bacterial volunteers also inspecting sites for harmful algal blooms, which we'll talk a little bit more about in just a moment. So the reason that we look for E. coli is that it is a relatively good way to indicate if interacting with the water is healthy. So E. coli is a bacteria that is present in the digestive systems of animals, including mammals and birds, and is introduced to waterways through runoff. So if you've got pet droppings that get washed into the water. There can be livestock. You've seen all the Canada geese. Each one of those geese can poop, I think it's 1.5 pounds a day. So that's introducing a lot of fecal matter into the water, which can include E. coli. Also things like broken septic tanks and sewage systems that are, aging can contribute to the introduction of E. coli into our waters. So the bacterial action team goes out once a week, they collect their water sample, they bring it back to the lab where we feed and incubate that sample, and then we will quantify the number of colonies that are present within that sample. So once we have all this data, we have to kind of have something to measure it against to figure out whether or not this is actually good. So the state of New Jersey has put together these surface water quality standards for each of the parameters that we measure. So for water temperature, we're looking for waters that do not exceed 30 degrees Celsius. Nitrate is an interesting one. There is actually no surface water quality standard for nitrate in the state of New Jersey, but we use the drinking water standard, which is 10 parts per million as a substitute. Phosphorus should not exceed 0.1 parts per million. So we actually measure orthophosphate, not total phosphorus. So the comparison is a little bit hard to do. pH is a range, should be between 6.5 and 8.5. And turbidity, which is the clarity of the water, should not exceed 50 nephelometric turbidity units, which are similar to the Jackson turbidity units that our volunteers use. DO, which stands for dissolved oxygen, is one of the most important parameters that we measure, and that should never fall below 4 milligrams per liter. And then finally, E. coli levels should not exceed a geometric mean of 125 colonies per milliliter over 5 samples within 30 days, or a single sample maximum of 235 colonies per 100 milliliters of water. So those are the surface water quality standards that we are comparing our data against to determine whether or not our waters are healthy. And so one of the other things that we look for are these harmful algal blooms. Harmful algal blooms are actually caused by a bacteria, which is why our bacterial action team looks for these, is responsible for this monitoring. They're not an algae, but they are a photosynthetic bacteria that are an essential component of the ecosystem and are supposed to be there. And the issue, as with many things, is when they're out of balance. So some of these cyanobacteria can produce toxins, which can cause issues for humans and for animals. It can be as minor as skin irritation or some digestive upset, but it can be much more serious as well. So this is an issue that has become more and more prevalent in our area because of kind of this recipe. With climate change and increasing temperatures and increasing stormwater runoff, we're getting inputs of nutrients and sunlight, which are creating perfect conditions for these cyanobacteria to grow. And so this is an increasing issue in our area that we are working with DEP really closely to keep track of and manage. Okay, so let's talk a little bit about the waters here. In New Jersey, it is it's the 5th smallest state and the most densely populated state. In our state, we have over 19,000 miles of streams, over 47,000 acres of lakes, only 60 of which are natural, I think. 650 square miles of estuaries and 470 miles of ocean, and lots of wetlands. New Jersey is one of the most hydrologically and I want to say geographically, but geologically, thank you, geologically diverse states. So there's a lot going on and there's a lot to monitor. New Jersey DEP splits the state into these 958 hydrologic units to determine, just to break up the state so they can do their assessments. So our area is right in here. So we have water management area number 10 and the bottom half of the water management area 11, which includes these hubs. All right. So I wanted to give a little bit of a historical background of the water quality in New Jersey since we've been monitoring. So this is some excerpts from the State Water Quality Inventory Report, which was published in 1992, the year that StreamWatch began. So this report was conducted over an 11-year study period and a 7-year study period. So they took those 2 data sets and did these analysis. In general, they found that the dissolved oxygen was increasing, which they attributed to a decrease in the input of oxygen demanding materials. And this was from a an effort of this on the part of the state in the 80s and 90s to improve sewage treatment processes and plants throughout the state. So this report is one of the first that's indicating that those actions actually did make some changes in the water quality. However, they also found increased dissolved salts. The nutrients showed some mixed trends. There was some up and some down, and the causes of those trends were pretty unknown at this time. And so this little chart here is showing in the 11-year data set, nitrogen mostly went up, but did go down sometimes. In the 7-year data set, nitrogen went mostly down, but up sometimes. Dissolved oxygen went up in both data sets. Organic nitrogen went down in the 7-year data set. Phosphorus was kind of half and half in the 11-year data set, but mostly up in the 7-year data set. And ammonia was up in over 11 years, but down over 7. So interesting. Flash forward 10 years to 2002. And this is the first time that we've got what we call an integrated report, where they are putting together the list of streams and rivers that are, they're putting together their assessments with a list of streams and rivers that need protection or improvement. So from the data that they collected for this report, they found that 84% of the non-tidal streams and rivers in the state were non-attaining or not supporting at least one of their designated uses. So the designated uses can be things like drinking water, recreation, fishing, aquatic life, that kind of stuff. So 84% of the streams and rivers that they monitored were failing at least one of those tests. They did, however, find healthy dissolved oxygen levels. Temperature was generally pretty good. You had 87% of the samples of the sites supporting, reaching that threshold, and only 13% exceeding it. Phosphorus was a little bit more mixed. We had 55% attaining and 45 non-attaining. And TSS, our total suspended solids, which is related to turbidity, was mostly good. 94% were attaining and only 6% were not. And this graph here is just showing, let's see if I can zoom in a little bit. It's showing the number of river miles that were exceeding the standard for each of these parameters. So you can see fecal coliform was by far the most problematic, followed by phosphorus and then pH. So this is a little bit more technical, but if we look at sublist 5, which are the streams that are, oh, I'm forgetting now. Sublist 5 is the streams that are impaired. We can see how many are monitored and what their overall support looks like. So then we'll fast forward another 10 years to the 2012 integrated report. In this report, they found the conditions to be relatively stable from the previous one. There was improved dissolved oxygen and nutrient conditions since the 1980s. Again, that was attributed to the sewage treatment upgrades that happened in the 80s and 90s. There was, however, a decrease in the conditions related to nitrate, meaning more sites exceeded that nitrate standard. So here we have a graph that's showing us the different designated uses that I mentioned earlier, and the percentage of sites that in green supported that use, in red did not support that use, And in yellow, we didn't have enough information. Yep, so here, these are the uses that I was talking about: the water supply, recreation, aquatic life, shellfish harvest, and fish consumption. In this report, they also provided a list of the top 10 contaminants or reasons for non-attainment within the state. And again, we can see fecal coliform is still that #1, although much more closely followed by arsenic this time. And total phosphorus, that's a TP here, is still pretty high up there. In general, I'm ignoring the fish consumption part because our waters are not rated for that. The waters that the Watershed Institute monitors. So, but the aquatic life are certainly impacted by the levels of DO, pH, and TP. So that's 2012, and now fast forward another 10 years, kind of. This is the data from the 2018-2020 report, which, thanks to the pandemic, was a little bit delayed. They combined the last 2 reports and are now working on the 2022 report. But in this most recent report, we see these general trends. Phosphorus is decreasing, nitrogen is decreasing, nitrate is increasing, dissolved solids and chlorides or salts are increasing, and metals and ammonias are decreasing. So that's not so bad. And if we take a look at the designated uses over here, we can see, sorry, just a sec. The number of assessment units that do not support and support in the green, and the blue is the insufficient data. So the amount of insufficient data has definitely decreased since that previous graph. And I think we could say that the supporting numbers have increased a little bit, and it's certainly flip-flopped around in this one. So, okay. So now I wanted to get into our report cards. The Watershed Institute collects this data through our volunteer program, and we produce a report card for the watersheds every 5 years. So it takes into account data from the last 5 years. And so we'll start with temperature, which in general is pretty good throughout our region. The dots are the monitoring sites themselves, and then the areas that are shaded are the sub-watersheds that those monitoring sites represent or characterize. So you can see most of these sites are showing green with just a couple red, one orange, and a handful of yellows. So generally pretty good with temperatures around the state, around our area. This says overall scores, but it should say nitrate scores. This is the nitrate for our area. Mostly fair in this orange region. A couple of places that are okay with nitrogen, and then a handful of good ones as well. And again, the standard for nitrogen is 4 parts per million. Yeah. And the standard for temperature should not exceed 30 degrees Celsius, 31 degrees Celsius. The phosphate scores in the area were not so good. Lots of red happening here. Of course, the standard for phosphorus is really low. It's 0.1. So that's why we're seeing a lot of red here. pH is a pretty mixed bag. And turbidity is generally doing pretty well. in our area over the past 5 years. We can see, however, like this orange area up at the top right is where we had some issues with a quarry that was releasing effluent into a stream and causing some spikes in turbidity. And so that's reflected in this 5-year report card for that area. That's why that one's orange. Dissolved oxygen, much like the integrated report reported, is doing fairly well throughout the state. And that is also the case in our region. Oh, I'm sorry. This is the nitrate. So this makes more sense actually, because the nitrates in Trenton are much higher. Trenton is downstream of pretty much everything else. And so everything, all of the nitrates that are getting washed into the water in these upper watersheds are flushing down into Trenton, which also has more impervious cover. So it's getting more nitrogen that way. So yeah. The bacteria scores are not great. There's, as we saw in the charts from the integrated reports, fecal coliform has consistently been the biggest issue in non-attaining waters in the state. And then we have our macro scores, which you can see we have less data for. There are less data points, less sites that are monitored. And so we have just less information, but in general, not so hot. Overall, this is showing a trend towards the middle, and that is also reflected in the integrated reports. There are less excellent sites and less poor sites and more good and fair sites. So overall, we're middling out. So now we can take a look at our data, what we do with it, and what it's telling us. So data is, useless unless the people are looking at it and doing something about it. So the first thing that we do with our data is we produce those water quality report cards, which are those maps that I've just gone through. Those are available online on our website, and you can go through our water quality report card, and then you can actually play around with this dashboard and look more closely at your area or your monitoring sites to see how they've scored over the past 5 years. We also use our data to work with municipalities and local decision makers to address specific issues in water quality in their areas. And we use our data is added to DEP to help them produce their integrated reports. So okay. So there's the 3 teams. In addition, this year we've added StreamWatch Schools, which is a new program. And we're hoping to get more students and teachers out into the field and collecting their own data so that we can just start earlier and have more kids participating. In an effort to increase the quality of our data and the consistency of our data, we've made some of these recent changes. So the bacterial team does their 3 5-week sampling sessions over the summer. We've recently added the visual assessment for the harmful algal blooms. We've also added data collection using ArcGIS program Survey 123, which helps us get some more precise measurements of, or precise location information, as well as like pictures of potential algal issues. We ask the volunteers to bring several samples back to the lab, which we can then test for nutrients as well as bacteria. And this past summer, we added turbidity. So we were measuring that as well. We have started using interns from the High Meadows Environmental Institute at Princeton over the summer to help us with the data and with the lab work and data analysis. We've also been working closely with DEP to report any harmful algal blooms that might be happening in our area. Yes. And then finally, for the bacterial action team, we've started just this past summer publishing our data on a website called Swim Guide, which is based in Canada, but is a worldwide mapping program online. You can go to swimguide.org to find different places where you might want to go swimming and what the water quality is like at those places. So we've added our sites to that list this past summer. The biological action team is working on a new protocols that include testing of our volunteers and accreditation so that we're making sure our data is collected properly. We're using a standardized rapid bioassessment protocol designed by the EPA. And we've been alternating for the past couple of years, we've been alternating tiers. So these tiers have to do with the level of data accuracy and whether or not it can be used for regulatory purposes. So 3.2 tier is a little bit lower, and that can be, that's where our volunteers will actually identify the organisms themselves. And the tier 3.3 is where we're sending those out to the independent lab for more specific identification down to the genus or sometimes species. So how do we make sure that the data that we're collecting is useful? We use a quality assurance project plan. So according to EPA, the Quality Assurance Project Plan, or QAP, is a written document that outlines the procedures a monitoring project will use to ensure that the samples participants collect and analyze, the data they store and manage, and the reports they write are of high enough quality to meet project needs. So this is basically, we have to write out a plan of how we're going to monitor, how we're going to take care of the data, how we're going to make sure everything is working. So it's really taking our study design up to the next level. We're making sure that we're preventing error, or trying to prevent errors before sampling begins by doing trainings in the field and by doing accreditations. We have some quality control measures that are put in place, such as re-identifying some of the volunteer identified samples, or auditing volunteers while they're actually going out and sampling. We'll send a supervisor to make sure that that's happening correctly. So the first QAP that we had was for the chemical action team, and it was first implemented in 1996. It's not currently active, but that's because we're looking at some changes. So we'll talk about that more towards the end. But because that QAP is not currently active, our chemical data is not submitted to DEP for regulatory use. The biological action team, however, does have a QAP in place that is active, which was implemented in 2007 and is actually scheduled to be updated this fall. So we're working on that one. All right, so let's talk a little bit about like this actual 30-year data set. Altogether, there were 12,736 data points. So that's each time a volunteer went to a site, that's one data point. Our region, again, is kind of the Midwest of the state. So you can see we kind of straddle this high gradient and coastal plain habitat types. However, our data is pretty skewed towards the high gradient sites. We've got here the number of visits per site per year and the number of sites visited per year. So you can see here, this graph is essentially showing that the number of sites that we have been monitoring has consistently increased over the past 30 years. However, the number of times we visited each site took a nosedive in about 2010. And that is because our chemical action team used to go out twice a month, and that was reduced to once a month in 2010. So that's that. We also took a look at how many data points per site we had and how many years each site was monitored. So these sites, these are the sites across the bottom here in alphabetical order. So it's not particularly significant, the order. On the left, we have the total number of visits for that site, or total number of data points for that site. And on the right, we have the total number of years that site has been monitored. So you can see these yellow points here are the sites that have been monitored for 30 or more years, and we'll have 7 of those. We have 15 sites that have been monitored for between 20 and 29 years, 14 between 10 and 20 years, 14 between 5 and 10 years, and 25 sites that have been sampled for less than 5 years, which means either we stopped sampling those sites or we've increased the number of sites in the past 5 years. So another way to look at this, since this doesn't, this order isn't necessarily significant, we can take a look at the different hydrological units or by municipality. And so looking at the hydrologic units or the sub-watersheds, we can see that the lower Stony Brook watershed is by far where we have most of our data. And that makes sense because it was the Stony Brook Millstone Watershed Association for most of its history, and most of our sampling has been done right here in Princeton. So the municipalities here, this one here is Princeton is the highest number of data points. Yeah, we can see like the upper Assunpink hydrologic or subwatershed doesn't have a lot of data points, neither does Moore Creek. So this helps us to identify some of the spots where we can put some more effort. Alrighty. Okay, so patterns and trends in the 30-year data set. Brace yourselves. So the first thing I did was just like throw all the data onto a graph, and there are some things that you would expect to see. This is a graph of the water temperature over 30 years, and you can see there's some seasonality to it. It's peaking in June and dropping in December every year. So that is what we would expect. We can also see that with the dissolved oxygen, which is very correlated to temperature inversely. So we see drops in June when the water temperature is high and peaks in December when the water temperature is low. And that's because dissolved oxygen or cold water can hold more dissolved oxygen. So again, we can see these patterns that we are expecting to see. But then we'll look at something like all of the nitrate data. And this is, well, so the first thing you can see right off the bat is the number of data points decreases right around 2010 when we do that change in protocol from two visits per site per month to 1 visit per site per month. So you can see that drop pretty drastically here. But then the other thing that we're seeing here is really our detection limits. So the way that we collect this data is we give volunteers kind of a checklist. Is it this? Is it this? Is it this? Is it this? And so you can see that their answers really fall in line with those options. So that's more of an indication of our protocols than it is what's going on with the nitrate in the water. And then there are some interesting things that show up, like pH, which I wouldn't have expected to see any patterns in, but at the beginning of our sampling period here, we do see some ups and downs happening. And then that pattern starts to become more chaotic and kind of dissipate as we get less data points. So again, yeah, so again, that's pretty obvious, that the change in protocols there. But the patterns here are interesting and something that we would then look into a little bit more. So for example, with the temperature, we'll split that up and we took a look at the averages. Let me see if I remember exactly what I did here. We took a look at the monthly average for each year of the highest highs, the summer months with the highest temperatures, and the winter months with the lowest temperatures. We plotted those out to see if there were any trends. And so up here we have the summer months. There's May, June, July, June, July, August, and September are these top ones here. And the bottom ones here are the winter months, which are December, January, February, and March. And so these trend lines are interesting because we can see like the summer month temperatures are increasing slightly, but they're increasing. And if we look at the axes here, we're starting at about, what do you say, like 22 and ending up at 23.5, 24. So that's a pretty significant increase in temperature there. The winter months is a little bit interesting. We do have some months that are trending upwards. I believe this one here, this top one here is March. But then we do have a couple that are trending downwards. So with climate change, we would certainly expect to see some of these changes, and perhaps we would have expected to see everything going up. But we do see some kind of widening of the extremes, which is interesting. So then we also took a look at the number of times the data that we collected showed an exceedance of the standard. So these are a little bit tricky to see, but temperature only has just a couple of little bumps right over here. And we can zoom in a little bit to see that. Nitrate is even harder to see. I think there was maybe one little bump here in 99. Phosphate, unsurprisingly, 100% of our data points exceeded that 0.1 parts per million standard for all 30 years. pH is kind of trending upwards here. We can see, started pretty low in 92, and the number of exceedances, or the percentage of exceedances over the number of samples, has generally increased. Turbidity is less obvious, but again, you can see there's some increases in the 2010s and 20s. And same for dissolved oxygen. So we are seeing, in general, the percent of times that we go out and find that the parameter is exceeding standards has increased over our 30-year period. All righty. So mostly when we start looking at this data, what we end up with is really more questions. So here I have some plots where we were taking a look at the relationship between the different parameters. So this is hard to tell, but I just can't. I just wanted to show the different types of distributions that we were finding. And this is, again, when you throw in all of the data. So it's just, bringing up questions. Of course, you can see this relationship between temperature and dissolved oxygen, which we expect and do find here. But the rest of these are not quite so clear. And so we can break it down into sub-watersheds and look a little more closely. This is the upper Assunpink watershed, temperature versus dissolved oxygen, and you can see that trend pretty strongly there. One of the things that came out of the data, as I pointed out earlier, is sometimes it's really just pointing out the detection thresholds. So the methods that we currently use for measuring phosphates do not allow us to estimate at the level below 0.2 parts per million. So that's what we're finding. All of our data is just right on this line because that's as low as we can measure. Over the summer, we collected similar data, but using our lab equipment, and we're able to get some much more precise measurements here. So you can see this is the 0.2 here, and we've got so many data points much lower than that. And this is the standard here, this 0.1. So we can really see that those are below the standard. Okay, so some of the limitations of the data that we've been looking at and reasons that we have more questions. Of course, this is a volunteer water quality monitoring program, and so there are inconsistencies between volunteers, between methods, or between sites and time of day of sampling and consistency of sampling and all of that. So that is part of the bag with volunteer monitoring. Also, as we were just talking about, the precision of our methods is not super high. And so that's something that certainly restricts our ability to interpret the data and see what's actually going on. The other thing that comes with volunteers is trying to make sure that the equipment that they're using is maintained, is cleaned, is replaced when needed. If we find outliers, it's entirely possible that that volunteer just forgot to get new reagents and they're using expired reagents. And so there's those kinds of confounding factors that are in the data that we have to kind of tease out. There's also a limited scope. We don't have continuous monitors in these streams. So we don't have continuous changes. We don't have the data to see how the water is changing over, continuously. And we are limited by the ability of our volunteers to actually access the water and get in there and sample macroinvertebrates. So, and then of course, there's always data entry errors and human error in filling out the data sheets and entering them into the database, in pulling them out of the database and putting them in Excel to analyze. There's room for error in all of that. So those are some of the limitations of the process of collecting our data. The process of analyzing our data also has some limitations in that all of the data points that I used for this presentation today was all of the data points that we have. But that means it's a mixed bag. So we have data points in streams and in rivers and in lakes and in ponds, and I think even in some canals. So we're not necessarily comparing apples to apples here. We have to make sure that our data is normalized in some way. So we saw the drastic changes in the charts between Before 2010, when we had double as many data points, and after 2010, when we had less. So when we're comparing kind of ratios there, we have to make sure that we're accounting for the decrease in effort, essentially. The analyses that we did for this presentation are also not necessarily spatial, not showing spatial trends. So we're not looking at as you move south, do temperatures get warmer kind of thing. Not that that would happen in our very small area, but we're not looking at those kinds of changes yet. Another issue is it's been 30 years and technology and people have changed over that time. And so that means that the data is stored in a bunch of different ways in a bunch of different places. And so pulling all of the data together and making sure that it is of a high enough quality for us to actually use is a limitation in and of itself. And then, of course, this data is not incorporating any of the contextual data that we would use to determine impacts on these water qualities. So we're not looking at precipitation. We're not looking at the surrounding land use. We're not looking at impervious cover or population density or any of those things. So those are certainly things that we would want to compare with our data to see if there are any correlations there. There are also other types of data that I was not able to get into for this presentation. So this is just a quick show of the biological data that's collected by DEP for our regions. There's also increased salts that we don't currently measure, also from the integrated reports, or the HABs that I haven't even looked at yet. So part of what we're doing with StreamWatch is trying to figure out how we can improve our data, how we can improve our methods. Looking forward, we're hoping to use digital meters for our chemical action team to get some of those more precise measurements. We're going to ask our volunteers to actually grab samples of those waters so that we can analyze them here in the lab with, again, our more precise in-house methods and equipment. We're also launching StreamWatch Schools and working with Stroud and Limnotech to build a data portal where all of our StreamWatch data and the StreamWatch Schools data will be accessible online for just the general public to be able to access and take a look at. So the goals of StreamWatch in general are to increase, do some online mapping and produce the municipal report cards, which we went through earlier. We're hoping to expand into a lake monitoring network and perhaps a continuous monitoring network. And we're looking to improve the quality of our data by improving the study designs, creating co-ops, and auditing existing methods to see where we can improve. Things that we're looking for to see if we've made it. We're looking for an increase in the number of volunteers, an increase in the number of data points collected. We're also, of course, looking for those deliverables that were mentioned, the reports and projects and that kind of thing. And we're just hoping to increase local knowledge of our waters, engage citizens, and help local decision makers improve the health of our streams. So just a quick snapshot of this data portal that I mentioned. We've been working again with Limnotech and Stroud to develop this portal, and it's based on the Monitor My Watershed system that already exists. So you can go to monitormywatershed.org to check it out, and you should be able to find a couple of our StreamWatch Schools sites that are up there. And last but not least, you can be a stream watcher too. Right now, we are in the middle of our biological sampling season. But we are looking to begin training new cat volunteers and hopefully to implement the meters that we've just purchased sometime soon, and certainly by next year. Yeah, we always have room for people over the summer in the bacterial action team, families, friends, anyone who's interested. Take a look at our website, become a member of the Watershed Institute and support our work, and volunteer for StreamWatch and help us collect this data. Thank you. I think that's all I have. I guess we can go to, I didn't leave much time for questions, but let's do that.
Thanks, Jian. That was awesome. So we do have a couple of questions in the boxes. So that are popping up as anonymous attendees, but is the seasonal pH differential due to road salts is the first question.
That's a good question, and we don't know. That's the contextual data that we're missing in this data set, of course. Like we just, based on the points that I've got here, I cannot say that.
Yeah, I mean, we do know like likely suspects of things that can affect pH. We know for sure that, you know, how acidic rain is can absolutely affect pH. We do know that geology is a very big driver of pH, and that's all under natural conditions. You know, rain, fresh water in general, just exposure to air tends to be slightly acidic. Pollutants in the air tend to make the rain more acidic, depending on what the rain is washing over. On the human impacted land, it can become even more acidic. We do know that salts can increase the alkalinity, though, of water. And so there are definitely studies showing that pH will go up. You know, if a water source is increasing, you know, a salinity is increasing. You know, we haven't correlated exactly. It was super interesting to see such a strong pattern across so many sites.
Yeah.
Because it's such a diverse set of sites. And, you know, if your water is infiltrating into the ground and percolating through the ground to your true groundwater, which interacts with the stream, then it's definitely having, you know, a different impact on your stream, on your water pH than it is if it's not going through the ground. So infiltration is a big deal. And if your geology has, you know, the minerals that dissolve, that go in, you know, from the rock as it percolates, goes into the water, has a buffering capacity. So, you know, the chloride alone from a salt is not going to necessarily have a big effect on the on such a strong seasonal pattern. But it will have an effect. But it's more of like what happens when you produce that chloride. You know, did you create a buffering mineral when you dissolved that salt, like a phosphate? We do know phosphates are high, but we just, you know, we have to start to kind of tease some of that out. I was surprised about how strong the pattern was.
Yeah, for sure.
You know, the outliers were not incredible outside of that pattern. But we do know some other things that we need to kind of look at and start to tease at before we can say, you know, because some of them were quite high, you know, up near 10, so, you know, the pH of 10 is really alkaline. So yeah, these are the things we really need to start to look at. Now that we can look at this data set as a whole, we need to say like what's making that swing so strong. And so that New Jersey has a diverse geology, you know, believe it or not, and it's actually got a just as Jian said, you know, from top of the state to bottom, we go from high gradient to, you know, to pinelands to low gradient coastal plains, which and that even within central Jersey, our StreamWatch network covers all of that. So we should see some differences in pattern. I would have expected, but we need to tease some of that out, see why we have some really strong patterns.
Yeah, for sure.
So second, we had a question about the trend for increased turbidity, and is that due to increased development in New Jersey?
Again, that's the same kind of thing. So we just don't, in this data set, don't have the comparative data, like the land use and impervious cover and development information. But yeah, that could certainly be one of the reasons turbidity has increased. It could also be, like Steve was just talking about, the geology and the erosion of the minerals in our area and just time. So yeah, so that's another thing to tease out, another factor to look at.
Yeah, I would add that, you know, turbidity during rain events is sort of a naturally occurring thing, even if you remove humans from the equation. But we do know construction sites, and you know, you just dig a hole in your yard and you're going to create a huge turbidity problem for the water that runs through your yard during the next rain. So we know that our activity really impacts that. I would say that yeah, as we impact the land more and more, we decrease the stabilization of sediments as a whole. But then also, I don't think there's there's very few water quality indicators right now that we can't connect to just the stormwater, you know, the rain precipitation volume and rate. Yeah. So we're getting faster rain, you know, larger volumes of rain in smaller, much larger, higher rate precipitation events. Yeah. And that's, you know, in the extreme event of a hurricane that erodes a house away, you know, let alone, you know, the banks of a stream that have a decreased buffer. So yeah, almost definitely. But, you know, where we are seeing things stick out, Jian was pointing out, and our staff over the last few days have been really looking at, wow, we need to really start saying, you know, is it one or more sites that's driving some of the trends? And there's so many factors, right, to all these water quality. You know, what was the precipitation like around that? What were the actual inputs? And certainly, you know, comparison to land use around each of the sites and watersheds that are showing the strongest patterns. These are all things we'll have to start to pull out.
Yep. So there's a question about, you know, what is our plan to capture this kind of contextual data as we go forward and as we look deeper into the data. You know, I'm not sure that we have a plan for that yet. We have done some studies on impervious cover, and so we have some of that data. Certainly probably needs to be updated at this point. There's a lot of data that's available, precipitation data and all of that. So it becomes a matter of just kind of finding the data and matching it with our information and seeing what comes out.
Yeah, and doing some of this can be a career all in of itself for one parameter against one contextual thing. So we're going to have to do it one at a time and lean on our partnerships. You know, I know there are a couple of people attending or were attending here. I saw in the beginning that are even part of our science department committee. So you know, I know his wheels are turning, and we have a committee meeting next week. So we'll be discussing a lot of like what are the most relevant things to look at and break it down and find the bandwidth to do that, because I could do 2 more PhDs.
Doing one.
Yeah, you know, on some of these questions. But yeah, we have to include that contextual data. You know, there was a question, what roles do we have in the remediation efforts? And is there an opportunity to engage volunteers in those efforts? And that's, you know, the second half of that question I'll answer first, and that's an absolute yes. You know, you know, we're really kind of thrilled that we're finally getting a chance to, you know, we've just been happy to collect the data and report our report cards as best we can and communicate with municipalities and residents and constituents what current states of things are. But state of the entire watershed is a big task, and it's an even bigger task to take a look at this size of a data set. So we're just super thrilled to have had the opportunity like get it organized into this so we can start saying what pops out, what questions can we ask. But we have been doing remediation efforts, over the years. We've been, in particular, the last six years, we put in a lot of green infrastructure, in place, and of traditional structural stormwater management, ranging from there all the way to floating wetlands and water bodies to catch pollutants that already exist. And so, that is, again, there's only so many of us that can do so much of that. But we're happy to be able to start getting into a position where we can share these things and the opportunities, so that we hope to engage more and more. We do have continuous monitoring devices out there, and now that we're getting a handling on that, we're going to need more volunteer corps, different teams, if you will, to help us do more types of monitoring and more types of restoration work, because we're reaching capacity for that kind of thing, because once you do that, we have to maintain it as well. So yeah, volunteers are definitely welcome.
And one of the things that we've done from the beginning is we really lean on our advocacy department to take this information to the different municipalities and try to involve them in their own remediation projects, and getting them to work together to do so. And so that's another way that volunteers can get involved, is through their municipal environmental commissions and promoting some of these projects, and talking to your neighbors and your neighbors upstream especially. And yeah.
Excellent point. And again, I'm seeing a couple of names on our participant list here that are just champions of that for us. Cannot thank you enough, when you put those efforts in, and they're resulting, for you can sort of flounder in this kind of field, right? Like, are we doing any good? Is it working, kind of thing? But we have great results when people respond to it and take ownership. But a really good result is, we have many of the stakeholders needed in, talking in the same room over the last bunch of months about planning regionally, so knowing that, like, it's not just about my town that's going to fix things, or what can I do here, but we have to start working together within a whole watershed. So within the Stony Brook watershed, we have I think all of the towns at the table. We have stakeholders saying, yeah, we have issues and we need to work together to solve these things. And so, that's going to be an important movement for us and all like-minded people.
Yep.
And then finally, we have determining the cause of the algal blooms in Lake Carnegie and downstream, and what happened next. So the algal blooms that we're talking about were harmful algal blooms, which just for those who aren't aware, is a little bit of a misnomer. So harmful algal blooms, in the context of these freshwater issues we've been having the last handful of years, is actually a cyanobacteria. So it's actually a bacteria that can photosynthesize. In form and function, they're the same thing as a true algae that you would usually want to keep to a limited level in your water body. And so they do much of the same things as a plant does, which means they need they need enough nutrients, they need a lot of sunlight, and they need water, obviously. So, the cyanobacteria play by slightly different rules, because they can do things, they fill a different niche. And so they've basically always been there, like almost all bacteria, in the background doing what they do. But something about our environments is shifting to favor them. They're out competing regular algae. We do tend to think, we do have strong evidence that it's the flushing, from our lands of excess nutrients. We tend to focus on phosphorus. I don't know if I personally am sold on that being the only culprit, but the higher temperatures, and the higher rates of flushing with stronger periods of drought in between. And I say drought very loosely there, might not technically be a drought, but having longer periods of, very small to little to no rain, followed by very big storms that flush a lot of those nutrients in, loads up a water body with everything a growing cyanobacteria needs. And then all of a sudden no rain makes it a little bit more stagnant. And the slower moving the water is usually will favor cyanobacterial blooms. There's a lot more complexity to it than that. But in general, I personally was extremely surprised to see such intense blooms throughout the Millstone River, including Carnegie Lake, because that's even during our dry times, that's a pretty large moving water body. And they're just not known to bloom really strongly in something like a river or a flowing stream, to the fact where we would have that kind of problem. So to my knowledge, we don't know why that happened there, whereas it was not happening, even though we were getting those blooms in lakes and ponds that we've been monitoring for years, they were nowhere near as high as those. So in my mind, it's still kind of an open question as to, was it the impoundments in the river that slowed things down enough? Were extra things sort of resuspended from siltation and sedimented sludges and that kind of thing that tend to change the chemistry, the water quality, especially under extreme conditions? Was it that? We don't know the answer. I do know, and I haven't been able to dive into it enough. So someone on the call may even know more than I do on the meeting. But I do know that Water Supply Authority was all over it, because it impacts water intake for drinking water, and DEP, and that they were coming up with some treatment plans that they were going to do up and down the Millstone. And I think they generally was a physical treatment plan. So using some sort of system that would sort of gather, concentrate the water volumes with the algae in it and basically destroy the algae, like physically taking it and breaking it up. So, but I don't know much more than that. There may be a lot more going into it. But we were busy kind of studying our own stuff at the time, and it only just happened. But it's something we're going to be paying attention to more and more.
For sure.
Jim, great question.
Well, before you jump into that, I just want to say, I know we've gone over time. If you need to leave, please go ahead. Thank you for joining us. We'll stay on just a couple more minutes and finish up these questions. Thank you.
Yeah, great question, Jim. I don't know if you could type in, because I don't actually remember the timing of the dredging, and was it just near the dam?
So the question was, did the dredging have any impact on the harmful algal bloom in Carnegie Lake this summer?
Yeah, the only reason I hesitate to say that was a cause, and again, I haven't looked yet with DEP or any of the actual collected data, where the most severe. I mean, I wanted to get in a kayak and do the entire river with with the right equipment to measure a few things to see where it was most intense and not. So I didn't see where it became more and less intense, but I do believe we had blooming above Carnegie Lake as well, outside of the area, certainly upstream of the areas that would have been dredged. So whether it was more intense downstream, I certainly could see that being a potential source. I'll say this, I say this often, but one of the things we don't talk about that's an important factor in photosynthesis period, but also in nitrogen fixation and some other processes, is dissolved iron, which doesn't tend to be a limiting factor in most freshwater. But if we're mobilizing extra iron and some other things that are limiting the other algae growth, cause them to not grow as well, or let the cyanobacteria outcompete them, they're certainly going to grab onto that iron, way better than your typical algae will. because of the nature of bacterial processes. So so dredging would certainly have the ability to remobilize some iron, and then as it flushes over dams and down riffles, oxygenate it a little bit, but which actually, you know, the low rain amounts we had would have lowered that ability, you know, for the oxygenation. So yeah, it could have drove higher HABs downstream, but I'm just speculating at this point.
Also possible that we just weren't able to detect changes in nutrient levels. Like I mentioned, the methods that we're using right now are pretty coarse and have some pretty low or rather high detection limits. So if there are changes happening below that, we wouldn't necessarily pick that up.
Yeah, good point. And again, being more of a bacteria you know, in form and function, the cyanobacteria are better at taking up nutrients under certain conditions than they will be able to take it up in mass, like better than most of the algae could. So I tend to think that's where they outcompete them. But then there's also just the high heat, you know, the high levels, the high water temperatures, and you know, is enough to maybe drive them into being competitively dominant.
All right. Well, I think that's all the questions that we have. Thank you, Steve, for helping me vet some of those. If you have any questions, please feel free to email me at streamwatch@thewatershed.org. We will be sending out the recording of this as well as the slides themselves. So probably in the next week or two as we process everything. So thank you for joining us.
Thank you, Jian. Excellent job. And I just wanted to remind everybody, the next technical Friday webinar is on road salt studies. And I don't know, maybe we'll look a little bit more into if anybody's studying that, particularly in New Jersey, and its effect on pH. But the link is in the chat to register for that. So thank you all for joining us.
Thank you.